Okay. All right, everybody. So take two. We're going to be talking about the ocean circulation, which is the second part of hydrosphere that we've been talking about since last time. So we finished talking about catchment area, watershed, but now we are on ocean circulation and all of the different impacts from humans. So if we take a minute to write this down, so ocean circulation and the ocean in general has two main parts that we're going to be looking at. The first part, the first layer, if you want, is what we call the surface current. And then beneath it is a much larger and slower. So this one is slow. Let me just erase that. This one's slow, and this one is fast. The top layer. So the top layer of the ocean, much like you have layers of the earth, you have multiple layers. The ocean also has multiple layers, and different things are happening during those, in those different layers. Like, for example, this first layer, which we call the surface current. This one's caused by wind. So take a look at, like, when it's a really windy day, the ocean looks really scary. Okay. But then when it's a very calm and quiet day and there's no wind, then the ocean's a lot calmer. They move the ocean horizontally, as you see. And they are also, the surface current is also affected by the rotation of the earth. So as in other words, the high tides and low tides of the moon. So for example, in the evening, when the moon is present, it tends to attract the ocean towards it. And then in the day, when the moon is on the other side of the planet, the tides will go back to normal, higher level. So that's for the top layer. And that's the one we see if you're standing at the ocean, or even like you're looking at something online or whatever. What you see is the surface current, the beautiful waves or what have you. But we do not see the bottom part, this one, the subsurface. You'd need to be literally in a submarine to see it or feel it even. Okay? And this one is what triggers the temperature in the world, the global, one of the things that global warming, one of the consequences on global warming. So let's look at the subsurface current caused by two things. Well, one, the density, but the density is changed by two things: the salinity, like how salty the ocean is or the water, and the temperature of the water. So here I was just drawing, I wrote down that the higher the amount of salt you have in water, the more dense. Because look what I wrote, look, see the drawing that I did here? Essentially something that is very dense, like this is dense. The particles are very compacted together, making it very dense. So it will easily sink. And here, not dense, so in fresh water, when you have fresh water, you do not have salt. Okay, so this here is fresh water, no salt. And this is salt water, like ocean. C'est bon? So this is important to remember for the next step for the ocean circulation. So fresh water, like let's say coming from melting glaciers, melting icebergs, that sort of thing, will cause the salt water to be diluted. And if it's diluted, that means it will not be dense anymore. It's kind of like if I have a glass of water full of salt, if I add fresh water to it, then it will be a lot less dense because the particles will spread out in the liquid. So that's for the salt content. The higher the salinity, the higher the density. And the other factor that play with density is the temperature. And it's the opposite. The lower the temperature, the more dense. And here is an example of a drawing. The cold air, you see the particles tend to be closer to each other. Whereas vapor, which is hot, the molecules tend to be spread out more. So because in one area, as you see here, I have more particles, this makes cold air a lot more dense. So think about, girls, think about the in your house, if you have a house, or in generally speaking, where is it colder? In the basement or on the top floor? Where is it colder? Anybody? No.
This is at the top.
The colder is down in the basement. It's always colder in the basement.
Okay.
And then, like, even think about the freezer. If you open your freezer, the cold air tends to sink down, right? As opposed to go up the way it does for heat. So the same concept of cold versus hot happens in water and the ocean. The cold water, such as in the North Pole or what have you, is very dense. Particles are closer. But hotter water or warmer water, particles are starting to spread out. So in one little area, I would have less water, making it less dense. So I just rewrote the same thing that you see here, but in words instead of arrows. Increased density means more salts and cold temperature. And this means water sinks. I wrote here, and the opposite is true, meaning if I have warmer water, then it'll tend to rise. And if I have fresh water, which is less dense, it will also tend to rise. Okay. Any questions so far?
No.
Okay. So we come to this point where we call it the thermohaline circulation, which is the essential circulation of heat and salt, you see, of the ocean. Thermo is for heat, haline salt. And we have this lovely map of the Earth with all the various directions of the current. So as you can see, you have the cold water coming from the north. Because it's cold, it tends to sink to the south. Okay? But as soon as it starts hitting the south, there's a bit of a fluctuation. And this cold water now is no longer cold. It's starting to warm up. That's why it goes back up around India. And further, of course. As it does that, it cools down over here. Because we went this warm temperature means it's going to rise, but it's cold up here. So since it's cold up here, it's going to sink again. It's a constant cycle. And I have an animation to show you about that. This one. Thermohaline circulation. So you see all the, you have the cold current. Notice the cold. See that? This is all the west of Canada and California and all that. So notice how the blue lines represent cold. They tend to sink. They're heavy. They go south. But then they hit the equator. And then what? What happens next? Follow it, you see? Once it gets warm, a warm air, warm liquid rises. It's less dense. So it's going to go back up. See? But now it's too cold. It's going to sink. And it's going to get warmed up again. And the whole thing starts over and over and over. Okay, let me show you the deep currents. That's a nice one. You see? Now, where's the North Pole? There we are. Canada. Okay. Notice the movement. We have the ocean circulation. It's cold, therefore it sinks. Let's follow the line. Where does it go? And then it goes back this way. Go here and then go back up. So this cold water tends to sink, but then because on the way it falls into the Gulf Stream, which is really hot, it warms up again. So you have a section here that starts to warm up again. This, all of that, and it goes back up. Then it gets cold, it sinks again. You see? So it's a constant movement. And that's what you see here. So take a minute and write this down. The ocean travels, cold water sinks to the south. Then it warms up, it rises back north. Then the whole thing starts over and over and over. So the impact of this, without even realizing all this is happening around us, thanks to all this movement of the salt water going up and down and up and down, this is allowing our temperatures to be regular. Like it's not going to be here in the north. Won't be excruciatingly cold. It won't be like minus 40, 50 all the time. And same with the equator, it won't be over hot. So how does that happen? Well, all of this ocean, it's not just the water that's moving, it's also the mass of air above it. Like, it's also very logical. If I have warm water, how can I have a cold temperature on top? It would cool it down, and vice versa. So this warm water carries also warm air, and so like above it. And so you can imagine when this goes up, this warm weather makes the cold temperature a bit less harsh. It warms up. And then the opposite is true. Cold water and cold air come down to the equator, cooling it down. So in other words, if we didn't have this, in the equator, instead of having, 35-degree weather, it would go up to like 45. Okay? So having this circulation helps regulate temperatures above water. So the polar regions won't overfreeze and hot areas won't overheat. So now you understand. It's really a trickle effect, like a domino effect. The global warming coming from the ground. Remember the permafrost. When it starts to melt, you have particles of gas, CO2 and methane, go into the air, causing air pollution. And then you have water pollution. And then you have like all of it, the water pollution due to the toxic products from industry and so on. But let's not forget that these gases also create a greenhouse effect. So the greenhouse basically traps the heat into the earth, making the temperatures unstable. If the cold water from the polar area is too warm, obviously it's going to melt the glaciers, which is, I'll talk about it some more when we get to glaciers. This you don't have to write. I was just giving an analogy of what happens on Earth with the water currents. So say you're drinking a burning hot coffee, automatically you're going to want to add cold water or cold milk, right? To cool it down. So it's a bit like this. The burning hot coffee is like the ocean near the equator. And when it receives cold water from the north, like us, then it will help regulate the temperature. It won't be overly hot. Okay? And the opposite is true. If your liquid is too hot, is too cold, I can add hot water to it to regulate the temperature. So I wanted to show you. I know it's going to sound silly, but we have, let me just show you, I'll find it for you. In Finding Nemo, they have a subsurface circulation. In Finding Nemo, I'll show you. Did any of you watch it before?
No.
Finding Nemo?
No, I never watched it.
So I'll just show you a small clip. Oh boy, that's loud. Where he gets suckered into the subsurface current. Oops. Okay. Cool. Can you see it?
Yeah.
I think that's the one.
Dude, check it out!
I'm in a class. So watch what happens here. Look at this. Okay. So I know it's a little silly clip, but it holds a lot of truth in it. So Finding Nemo, as silly as it looks, has a bit of a reality to it. A lot of species migrate thanks to the subsurface circulation, and allows them to take them from one ocean, from one section of the earth to the next, which is really cool. And they can migrate. And that's how scientists found out that these species migrate, because they find remains of it in different parts of the earth and realize that there's something beneath that helps them, gives them a push, kind of like at the water park. If you go to the lazy river and you swim while you're in the lazy river, it's going to accelerate your swimming. Okay. Now back to what we were talking about here. And the last part for today is regarding glaciers, icebergs, and ice pack. So still about the hydrosphere, because this frozen water that is unfortunately melting. I'll give you a minute to write this down if you wish. Glaciers, pack ice, or ice flow. So if I look at the difference between a glacier, an iceberg, and pack ice. So one thing to remember, the glaciers are generally the largest, and they are on land. I am sharing the screen, I hope. Yes. So, and then the iceberg is a piece of that glacier that has broken because it melted, and then you have a floating iceberg in the water. Okay? And lastly, a pack ice are just really smaller pieces of ice that are floating around in the sea. For example, if I look at a polar bear affected by this, polar bear losing habitat. If you look at their habitat, so you see what he's standing on right here or here? These are all pack ice. So slabs of ice. Slabs of ice. As opposed to a glacier or an iceberg, which is a lot bigger. So iceberg, oops, versus see this? So that's an example, a glacier and a piece of it falls off. Let's take a look. And here's an example. So you have the glacier and then pieces of it that are icebergs, and those are floating in water. Whereas opposed to this one, the glacier, is actually the starting point is in the ground, as you can see here. Okay, so try to remember the difference between the two. Here's another example. You see this? The glacier is actually on the ground, even though there's compacted snow on top of it. That's a different story. But then layers that are fallen off or melted off, that's where the iceberg is. Okay. So I'll give you a minute, take a look. So essentially glaciers, you find them in the north, like in Norway, Finland, northern Canada, of course. So formed by compressed snow. Iceberg is a piece of glacier that breaks off, as I told you. And pack ice are just top layers of water that freeze, just like chunks, little chunks. And very important, they are all freshwater. Actually, 75% of the fresh water on Earth is all frozen in those icebergs and glaciers and pack ice. Questions?
No.
Okay, and the last piece for today is what is the impact of all of that we're talking about on melting? If it happens and it melts, now what? So this is where we get in trouble. And habitat, this, I think for me, the most important is those animals lose their habitat before we lose our habitat. And they can't find food to eat. So you see the polar bears are so skinny that they cannot survive like this.
Miss, will ecosystems like be lost? Like if that would happen? If like
Yes, I feel like the impact of this, I feel eventually we'd have sections of the earth that would be flooded so much. As if there's a reason. I think there's a reason for everything that Antarctica's frozen like this, or icebergs, or glaciers are huge. They carry so much frozen water. If they melt, we're in trouble. The sea level all over the world will go up by 25%. I heard about this recently in the news. 25%. That's not a joke. That can really cause major floods and essentially even maybe some areas would be lost because of it. Okay? I'm worried about Montreal because Montreal is an island. So we may feel the impact of this at some point, and then we'll feel it in the higher levels of the sea. So that's the key thing. Think of it as very logical because glaciers are so big and they have so much compacted snow. If that melts, it will definitely cause floods. It will definitely increase the sea level. Okay. And then if I look at pack ice, this will be a loss of habitat because like you saw in the picture, the polar bear, they needed to move around in their location. But if it's melting, they're really at a loss. I feel bad for polar bears sometimes. Even food is so hard to find. They have to let go of their little cubs because they can't feed them either. So it's really sad. You can take a look at what polar bears again, or little polar bears. There's one picture. Look how skinny this one is. They are starving. They should not be like this. That's not a polar bear. A polar bear is a big, chunky white bear, like the one you see in the Coca-Cola ad. A nice looking one. But the impact of humans on Earth is so big. It's like a trickle effect. It's got aftershocks after aftershocks on everything, whether it's ecosystems like these, animals, like everything. So here, pay attention, and this is a really important part to put a star next to this part. Notice how for pack ice, I didn't check this off, increased sea level. It's only the loss of habitat. The reason is pack ice is already there. Like it's already, basically you have the ocean, and then the top layer of the ocean is frozen because obviously it's very cold. So it's already there. That's why it doesn't increase the sea level. It's like if you have an ice cube and you put it in, okay, and then that ice cube melts, it will not make a difference because it's already been incorporated, okay? Whereas glaciers, they're on land. So if they melt, then that's an added ice to the water that wasn't there before. Okay? So that's why the major impact for glaciers is increase of sea level. And of course, I was getting to that in a minute, the slow ocean circulation. And it all goes back to what we talked about before, density. Was it this one? Yeah. So it plays a big role in this. So if I add fresh water to ocean water, the ocean water won't be dense enough, will not sink. And so it will not reach the equator as fast as it should. Okay. So this is why, like, some regions that are normally really, really hot, like I'm thinking Arizona in the States. Last year, I think they even got a bit of snow. This is not normal. It's not supposed to happen. Or Egypt, Alexandria. We're talking the pyramids here, the desert. And some parts of northern Egypt had a bit of snow. They were freaking out. So this is not normal to have cold temperatures like this. And over here today, even plus 12 on December 16. Where's this coming from? Well, like I said, we're getting warm water from the south, along with the warm air mass. Okay? It comes up to the north, gets colder. Technically, it's supposed to sink and go back south. But once it reaches the north, the water is no longer that salty. It's very diluted. So it's not dense. And because it's not dense, it can't sink as fast. And so it gets stuck up there, right? And takes time to come back down. So this is what I wrote here. Glaciers slow the ocean circulation because the density is lower. The density is supposed to be high. Same with the pack ice. Ocean water will be less dense, so it won't sink as fast. Okay? Maybe make a note. For water to sink to the south, it needs to be dense. So that means cold and salty. Any questions?
No.
Okay. Maya's still there? Maya? I'll check on you in a minute. And there's one last question for today.
I'm here.
Oh, hey. One last question about global warming. So global warming has caused the melting of pack ice at the North and South Poles. Explain how this affects the salinity and density of the salt water in those regions. How does this impact thermohaline circulation? So remember, pack ice is fresh water, like no salt. So if I add fresh water to salt water, it will lower the density. So salinity is reduced, it will be less dense, and then that doesn't sink. Okay? All good?
Yeah.
Okay, I'm gonna stop the recording.